Okay, so for example, say we wanted to calculate the flux integral of x cubed over 3, y cubed over 3, z cubed over 3 through the sphere of radius 2 centered at 0, 0, 0, oriented outwards. Okay? And the hint I'm given is maybe one of the big three would be a good idea.
Divergence theorem?
Why does the divergence theorem come to mind?
That's a volume. It's a volume.
Because it's a volume, right? Yeah, perfect. So if I think about the divergence theorem for a second, what does the divergence theorem say? This should be right in the top of your brain.
An integral of the divergence of your field with the volume is equal to basically the area integral dotted with the thing, right?
Close. Yeah, so this is the total divergence in the solid, right? Should be the flux through the surface, right? So that's the integral of f dotted with dA, right?
Yeah.
You guys cool with that? Okay, so this is going to be over the inside, right? The whole filled in sphere. And this guy's going to be over the surface. Yeah, just over the shell of the sphere, right? You guys with me on that? Mm-hmm. Okay. Which one did they ask me to calculate?
The flux across, so I guess just the surface.
They asked me to calculate the right-hand side, right? You guys see that? Mm-hmm. Right, so that's what they asked me for. They asked for calculate the flux through the surface. So that's what they asked for. I can use the divergence theorem maybe. How do I use the divergence theorem?
You need to check your properties first.
Good, you need to check your properties. Okay, what are my properties? Okay, so I need piecewise smooth surface and boundary, right?
Closed.
Your partial.
That seems super smooth, right?
Simple.
I need,
Partials that are
partials.
differentiable out on a bigger surface.
Yeah, I need the partial derivatives to be continuous and exist on a slightly larger thing, right? This thing is what? In x, y, and z. My vector field?
That's that works.
Specifically, it's a polynomial, right? In x, y, and z. Like each coordinate is a polynomial in x, y, and z. So those are going to have infinitely many derivatives everywhere, right? You guys cool with that? So check on differentiability. That's like super check on differentiability. Because it's not just on a slightly bigger thing, it's everywhere. And it's not just one derivative that's continuous, it's all of them. Right? Cool. What were you guys saying about orientability?
Is it positively oriented? Is that what I was looking at this morning?
Yeah, positively oriented is in like Green's or Stokes. On this, for the divergence theorem, you want to ask whether it's
Orientable.
yeah, the surface needs to be orientable, which if it's going to enclose a volume, it better be,
Yeah.
right? And it needs to be oriented which way? In or out?
Out.
Out. Is this oriented out?
Yeah.
Yeah, they told me that. Cool. Okay, so I think I've checked some assumptions, right? Okay, now what is the actual divergence of the vector field I have?
Once you calculate it, do you want me to tell you how to calculate it, or the calculation once over?
Either way.
X squared plus y squared plus z squared. Yeah.
Cool. Right, that's take this partial with respect to x, this partial with respect to y, and that partial with respect to z, right? That's, for reference, this guy. Right, take the idea of a gradient, dot with your vector field. So I got that I should be integrating over the sphere, right, filled in, x squared plus y squared plus z squared d volume. Is that d volume? Have I been forgetting a vector hat on that?
I think so.
No, that's a straight up volume. Okay, so how do you do straight up volume integrals on spheres? Do you do them in x, y, z's?
You want to convert to spherical first?
Yeah, oh hell no, right? So convert to spherical. So if you convert to spherical, you're going to have the integral, triple integral, right? Of that thing's rho squared.
And then that's going to be the conversion factor.
Okay, and then you need your conversion factor, which for spherical is rho squared sine phi d rho d whatever.
Yeah.
Pick an order. Pick your favorite order of the spherical things. This wasn't my favorite, so I'll go with it.
Then you can split it up into its line. Oh, you need your bounds.
Yeah, first I need my bounds. So starting from the outside going in, what's your phi?
Here.
0 to pi,
0 to pi. Why not 2 pi?
because it only does top to bottom.
Because you don't want to count this thing twice, right? So you want top just to bottom.
You can always throw 1/2 in the front and do 2 pi. No.
Next is 0
Don't
to 2.
do that.
Yeah.
The thetas go from
0 to 2 pi.
0 to 2 pi, and the
Rows go from 0 to 2.
y from 0 to 2.
The radius is 2.
Oh, cool. Okay, good. Where did I use this centered at 0, 0, 0 part?
That would be in
I don't think you need to. It's just a volume. It could be wherever it wants.
Uh-huh.
I guess it tells us a bit about how x squared, y squared, z squared, make sure it's all coming from a specific position.
Yeah, right? It's not so much these x squared, y squared, and z squared, right? It's the bounds that I was making. You guys see that? Because those bounds were centered up at the origin, right? If your sphere, for instance, is up over here, right? Your phis specifically don't go from the top to the bottom, right? They just go from
Oh dear.
there to there, right?
Oh, that's a nightmare.
Right? And then your thetas don't go all the way around. They do a similar thing. And your rows definitely don't go from 0 to 2. They go from wherever this side is to wherever that side is.
I got 4 to
And this would be a nightmare. Right? So if that was the case, right, if your sphere was centered up somewhere else, you want that change of coordinates thing, right, to move everything over there. Otherwise, this would be a disaster. Okay. Thank God it's centered at 0. Okay, now what were you saying, Corinne?
Split it up into each section.
Yeah, use that factoring trick, right? So let's see, I've got a function of rows here. I've got a function of phis there.
And then theta is just 2 pi.
And then there's a function of theta right here. Right?
This is just 2 pi in the end.
So I have here, that was a crap bracket. I have functions of my 3 variables. They're all multiplied together. So I can pop this into a 2 pi, that's my theta one, right? And then an integral from 0 to pi of sine phi d phi times the integral
0 to 2 and rho to the 4th.
0 to 2 rho to the 4th d rho. You guys all with me? Okay. What's the integral from 0 to pi of sine of phi? 2. So I got 4 pi times rho to the 4th antiderivative is
1/5.
the 5th, rho to the 5th, And then you're evaluating from 0 to 2.
So,
It's like 32.
So that seems like,
We have calculated by version, it's
32.
32.
okay, so I've got 2 to the 5th times 4 is 2 to the 7th
yeah,
pi
32
over
fifths.
5, which is whatever that is.
128.
Or,
Would you mind, moving
Oh, yeah, of course. Done? Hands free? What does this mean?
Means that,
More is fluxing out
Yeah.
of it than inward.
Yeah, it means that more stuff flows out of this vector. More stuff, right, flowing as this vector field goes out of this sphere, right? You guys see that? Does that mean that all the stuff is flowing out through the sphere?
no, the net.
Not necessarily, right? The net flux is positive. You guys cool with this?